Hello and welcome to our lecture on antenna theory. Today we have our general aspects of antennas, and we are going to define some general parameters to characterize an antenna. First, I start with explaining what an antenna is. When we look at a cable here, the cable has a guided wave in it. So we call this a guided wave. Wave. And in free space, we have a free space wave. Now in free space, we have a free space impedance of 377 ohms, as I explained last time. And in a cable, we have usually an impedance of 50 ohms. The impedance of 50 ohms states that the voltage to current ratio on the cable is a factor 50. And this one here states that the ratio between E field and H field is 377. When those values are different, this is going to result in a wave propagating through the cable in a big reflection, as the impedance 50 ohm and the impedance 377 ohms must be matched. So an antenna is nothing else but a device that matches the guided wave of 50 ohms to the free space wave of 377 ohms. So we have a wave transformer. There are several ways to organize these transformation, and one way is to have a line that's slowly gets wider, like this one. So we have an E field here. The E field propagates through my cable, and when the cable widens, it looks something like that, and the E field eventually unlocks from the cable and becomes a free space wave, as I sketch here. Parallel to the E field, there's also an H field going around that cables here. And without doing much of details, the H field keeps going like this. Again, also separates and forms a field which, now I have to draw it in 3D, which goes something like that here, and is perpendicular to the E field here. Remember, the E field and H field are in a plane wave far away from the antenna. They are perpendicular to each other. So. Well, why are antennas called antennas? Well, the name antenna comes from biology. When you ask a biologist what an antenna is, most likely he or she will answer, an antenna is this thingy that sticks out in the front of insects. So these are the sensors of the insect. And in Latin they are called antennae, or antenna in singular. And this name is adopted to the electromagnetic antennas because they look similar to the antennae in the biology world. In German, antenna for the insect is called Fühler, which basically means sensor. And in English, I think it's the same. So. Okay. Now let's take a look at the radiation of antennas. I explained that an antenna converts a wave on a cable into a free space wave. Now when we look at this here, let's say I have a cable, and then I attach to the cable, I attach an antenna. I'll just depict it like this. So, and let's assume that's a so-called isotropic antenna. An isotropic antenna takes the power that is fed into the cable and radiates it into space without any reflection. And the radiation is exactly the same in all directions of space. So we get a perfectly spherical radiation here. No? So I try my best to draw something like that. No? So, and from that radiation in all directions in the same way, I can try here. Well, let's do it like this. I can think about some kind of sphere going around here. And at this distance here, my radiation is the same everywhere. When I'm standing here and I look at my radiation, at this point the radiation is identical to this radiation, and this radiation, no? And this, and so on. No? That's what it's meant by isotropic, same in all directions of space. What is radiation? Well, how can we quantify this? We can measure the radiation by defining something like a radiation flux density or power flux density. The power flux density, abbreviated with S, is the amount of power per square meter flowing through a certain area. Let's say this is my area here. Then, through that area, I measure all the radiation that goes through that area. I collect all of them and I receive a certain amount of power. And that's my power received, and the power received per area, that's my power flux density, and it's measured in watts per square meter. So that's basically the definition of any density, is that it's something per square meter, no? Something per area. So this also, maybe remember, this is equal to my E field density times my H field density. That's just a side note. No? Okay. So, but how big is my power flux density S for an isotropic antenna? Well, we have to take a look at the distance here from the antenna center. Now it's a quite busy slide here again. Let's maybe take away some of these lines. So it doesn't look that busy. So I have a certain distance here, R. And we measure our power flux density at distance R. What is my power flux density at distance R? There's actually a very simple trick to figure this out. Well, we know at this point my power flux density is something called S, let's say. Then I know at this point and this point and this point, it's somewhere on the sphere here, it's always the same because it's isotropic. So I know no matter where I am on my sphere, I measure the same power flux density. So, and how is it related to the input power P? P radiated, let's call it. Well, think about it. When the power that's radiated over the antenna distributes over that sphere. So when I take all the power flux density of the sphere together, I get my total power R. Or other way around, my power P is distributed over this area of the sphere. And the area of the sphere is 4 pi R square. And this is my power that I radiate. Let's call it power transmit. That's better for me. So the transmitted power. So my power flux density makes sense, no? Is my transmitted power distributed over the whole sphere area. Then I get the total power back. No? So that's my definition of my S of an isotropic antenna. So okay. ISO. Okay, so my phone is ringing. Sorry. So okay. Now that's the way to figure out. Let's make it in black here. ISO. That's the way to figure out the isotropic radiated power flux density for an isotropic antenna. The isotropic antenna has a disadvantage. An isotropic antenna does not exist. There are several reasons for that. You cannot build an antenna with a cable on it. Where the cable on is, you already have a non-perfect symmetry already. And also when you have E-field lines always start somewhere and end somewhere. So there's no way to build something that actually gets a perfect symmetry. Nevertheless, this antenna is used as our reference. No, we always use isotropic antennas as a reference when we compare antennas. When I have one antenna that radiates twice as much as an isotropic antenna in one direction, and I have another antenna that radiates 5 times more in one direction than an isotropic antenna, then I know that the second antenna has 5/3 times more power than this first antenna, and so on. No? We come back to this in a second and you see how it works. So my isotropic antenna, even though it doesn't exist, is my friend. No? And the power flux density of my isotropic antenna following this equation here. No? So where my S stands for transmitted is still in German, I should change that. No? So that should be T. No? Okay, good. As I mentioned before, and here I have a big gap, which I don't really need, but that's the way it is. As I mentioned before, the power flux density is identical with the Poynting vector I defined before. No? My Poynting vector S is E cross product H, and this again is nothing else but E square over N naught, and has a certain direction. No? And sorry, somebody keeps calling me. Hang on a second. Okay, so Poynting vector is basically the same as power flux density S. So I can say, oops. Poynting vector is the same, what I explained in the last lecture, equals to power flux density. S, and then I take the Poynting vector absolute value. So, okay, good. S in my formula, when you go back here, see that the S is related to R by 1/r square. S, again, I'm on the wrong button here. S is proportional to 1/r square. So this is an important relation, because when we double the distance here, that actually makes the flux density 1/4. When we have 10 times the distance, my power flux density is only 1/100. So the flux density decays with the square of the distance, which is unfortunate. But that's a fact of life, and we have to live with that. No? So it's called the 1/r square law. No? Note that since S is E square, when you do the math, you will figure out that the E field and H field only decays with 1 over R over distance. So we can write E is proportional to 1 over R, and H is also proportional to 1 over R. So the E and H field only decays with 1 over R. Now let's have a small example of that. So you see how impressive the decay is. When I have a cell phone, and the cell phone radiates or transmits with half a watt, 500 milliwatt, then we can calculate the power flux density, and when we do it at 1 centimeter distance, we get a power flux density of impressive almost 400 watts per square meter. So that means when we are 1 centimeter away from the antenna of the cell phone, we get an extremely large power flux density, which is almost the same as the power density of a stovetop, where we have maybe like a couple of thousand watts per square meter. This is still not dangerous because in total my power is only half a watt. That means even when we have it close to our eye and our brain, our cell phone, the total amount of power we receive is only half a watt, even though the flux density is fairly high. When we go into 1 meter distance, then doing the math, well, it's factor 100. There's from here to here is factor 100. That means from here to here we have 100 squared, which is 10,000. And it's 1 over 10,000. So here now our power flux density is 39.7 milliwatts per square meter. When we go to 1 kilometer distance, then again we have from here to here we have factor 1000. That means from here to here we have factor 1 million. And it's 1 million smaller. That means from milli becomes nano. It's easy to calculate. And we get a power flux density of 39.7 nanowatts per square meter, which is fairly small already. However, that's usually an amount of power flux density we can nicely handle in a receiver. That's a common value we get at 1 kilometer distance. What's the power flux density assuming our cell phone is in geostationary orbit like a satellite? Well, we have to set our distance now to 36,000 kilometers. And that means, doing the math, we get about 3×10⁻14 watts per square meter. Extremely small value, a few femtowatts per square meter. That means when you have an antenna that is 1 square meter in size, receiving the power, you only get 3 femtowatts, and it's extremely a small amount of power. And that's a problem we have to deal with in satellite communications, since the transmitter and receiver are so far apart from each other. We deal with extremely small numbers or values of power. And now when you remember our lecture on information theory, you have several ways to get around it. Either you transmit with a lot of power, solution 1. Second, you bring your transmitter and receiver closer together. That also makes the power larger, as we will see next week. So we don't put it into geostationary orbit, but we put it into a low Earth orbit, which makes the distance only 400 kilometers or 500 kilometers. That would be nice. That would be a nice variation. We have here 400 kilometers, then this becomes much bigger. Or we only transmit very few data. Remember, when we have very little data to transmit, very small power is acceptable. And that's something, for example, we get in GPS satellites. In GPS satellites, you only transmit a timestamp, which has maybe 5 bytes. And this timestamp is such a small amount of data that we can handle these small amount of powers. A GPS satellite, the receiver actually gets much less power than the 30 femtowatts. It's less than a femtowatt. But it still works because we handle only a few bytes per second. That's all. Good. Now, real antennas are not isotropic. Real antennas radiate in one direction more than they radiate in other directions. When I have an antenna here, let's say this is my antenna, has some strange shape, and this antenna usually transmit maybe in this direction more than it radiates in this direction or that direction. That means the radiation density depends on the direction. So S is a function of direction. And what is direction? Well, direction we have to give in angles, because when we are sitting here in the center of my antenna, we have two directions we can define, and that's something I show you on the next slide. When we have an antenna here, and that's something we already defined for the satellite direction in the sky. It's the same idea, but here now applied to antennas. We have one main direction of the antenna. That's the direction of, usually the direction of main power. So doesn't have to be, but that's usually the direction of main power. Now, from this defined zero direction, this black arrow here, you can find one angle that deviates from that direction, which is my phi angle. That's the so-called azimuth direction. Remember, that's the same. Oops, it's the same in satellite communications in the sky. So I call it phi. Some people call it differently. And then there's a second direction. Maybe I draw it like this here, which gives the angle from the horizontal. And this is called the elevation. Let's go here. Having these two numbers, elevation, theta. Having these two numbers, elevation and azimuth, I have the direction of view of the antenna. And then I also have the distance r from the antenna, which is for the directivity not used. Now, with this two information, we can now define the radiation or directivity pattern of our antenna. And my antenna is somewhere down here, and it has a main direction of radiation up here. Then we can find out that the biggest radiation is in this direction, and it's marked in dark red and far away from the antenna. And then for other directions in the 3D diagram, we see the different amounts of radiation. 3D is nice, but it's difficult to handle on paper and in calculations. That's why it's usually only used for marketing purposes and not really for calculations. But you get the idea that an antenna radiates in different directions with different amounts. How to quantify this? Well, besides the directivity, there's something defined called the gain. And the gain of the antenna, capital G, is defined by this equation. The power flux density in direction phi and theta compared to the power flux density of an isotropic antenna. That means when I look in some direction phi theta, when I look in this direction here, theta and phi of the antenna, and I measure, let's say, 300 milliwatts per square meter, and my isotropic antenna, when I replace a real antenna with an isotropic antenna, would only give 100 milliwatts per square meter, then my antenna gain is 3. It's a dimensionless number. It's just a factor. My radiation is stronger compared to the isotropic antenna, or is smaller compared to the isotropic antenna. This could also happen. And as you see, the gain does not depend on the distance r, as it cancels out in the calculation. It's only a ratio between, well, it doesn't matter if I measure the ratio in 100 meters distance or 1000 kilometers distance, the ratio stays the same of the amount of radiation in this one direction or not. Please note, it's extremely common to measure the gain in dB, because it's a ratio between radiation in one direction compared to radiation in another direction. So it's a ratio, and ratios engineers like to express in decibels. That's why very common to find G in dB. And a second. It's very common to find a G in dB, which is just calculated in dBs by doing 10 times the decadic logarithm. So we have here, and I have to, so we have to say log 10 here actually of G. And this is called the gain in dB, and since it refers to an isotropic antenna, this decibel is usually denoted as decibel I. There's another I here, dBi, which means dB compared to an isotropic antenna. Some old guys compare to a dipole antenna, but it's really uncommon nowadays. That's why I not really mention it. So when you find a gain in dB, it refers to relates the radiation density in one direction compared to the isotropic antenna. Well, let's do some examples. A Hertzian dipole we can use, and a Hertzian dipole is nothing else but a small piece of wire sticking out in space. So when I have here a little wire and I apply a voltage to it, and then this antenna radiates into space. And this antenna doesn't radiate into space the same in all directions. For example, in the direction of the wire like this, it doesn't radiate anything. In this direction, it radiates more than an isotropic antenna. In this direction, it roughly radiates the same as an isotropic antenna. And when I look at this antenna from the top, let's say this is the top view of the antenna, and it makes sense that when looking at the antenna from the top, it radiates in all directions the same, because it's perfectly symmetric in this direction. There's no reason why it shouldn't. No? And that's why we get, depending on our view, if we look at the azimuth plane or the elevation plane, we get two different patterns. No? In the azimuth plane, well, let's start with the elevation plane. In the elevation plane, we get a pattern, as I said. In this direction, it radiates more. That's why in this direction, you get a value of 1.5 compared to an isotropic antenna. Whereas in that direction here, it doesn't radiate at all. That's why I get a value of 0. So we can now draw a line, and the distance from the center represents the amount of gain this antenna gives. And in case of the Hertzian dipole, this is a perfect circle in both directions, no? Like this and this. No? And when I have the top view, I see the azimuth pattern, and the azimuth pattern, since my antenna is just the stick in the center, it's the same everywhere. No? Doesn't matter what direction I'm flying around my vertical stick, I always see the same gain. And my gain is 1.5. No? It says here 1 because it's normalized. That's maybe confusing. In this graph, it's called E-plane pattern and H-plane pattern. I could also, no, I did the same. I could also call it, this one would be the elevation pattern. and this one would be the azimuth pattern. No? That's what it's often called. Because this one, elevation azimuth, refers to the horizon of the Earth and the elevation. No? And since you can rotate this antenna, that's not clear, and that's why people like to call it E and H plane pattern. E plane means my plane, and now I have to take away here the plane of where my E field lines are in. And my E field lines are, remember, my E field lines are in here like this. So my E field lines are up down, and that my plane is the one, the vertical plane. Whereas my H field lines, they are like this. No, they are in the horizontal plane. That's why this is called also the H plane. No? Okay. Good. Now, when you look at this pattern in 3 dimensions, you can actually see that the shape of my radiation pattern of the Hertzian dipole looks like a donut. You get no radiation up here, maximum in this direction, here, and it's perfect circular shape in the azimuth level. And there's a nice animation I can show you when my mouse works. Let's see if this works. Oh, I cannot open this here. Okay. But this is something you can try at home. Go to this YouTube video here, and you can see an animation how the radiation of a dipole looks like. I just took a screenshot of the thing, which is nice to watch. Now there's something called Gmax, which is the maximum gain achievable by an antenna. So when you look at an antenna, in some direction it radiates more, in some it radiates less. And we can now define a maximum gain, which is nothing else but, as it says here, the maximum of my gain function. For the Hertzian dipole, this is 1.5. And when we express it in dB, it's 10 times the log of 1.5, which is 1.76 dBi. That's my maximum gain. Please note something. I've written it here. Often, the gain G is written without direction information. It just says this antenna has a gain of 15 dB or 15 dBi. This actually means that this is the maximum gain of the antenna. Everybody says that, even though it's not mathematically correct. When somebody says this antenna has a gain of 15 dB, he or she means that the maximum gain of the antenna is 15 dB. I can show you an example of a real antenna I have here. This is a data sheet of an antenna you can buy, and you see here I do not have my stick, my notepad on the side. It's a 900 megahertz antenna for a base station, and this is the typical antenna you see everywhere in the city, stuck to posts and on rooftops and so on. It's a very typical antenna for mobile communication at 900 megahertz. Here you can take a look at the data, and in the very first line it says 13 dBi, which means this antenna has a maximum gain of 13 dBi and has a beam width of 120 degrees, which I show you in a second, tilt down angle and so on. And when you look here, give some more information, frequency band, the gain, as I said, the beam width, I mentioned this in a few seconds how this works. Impedance is my line impedance of the connector, which is usually 50 ohms. The maximum power it can handle, and VSWR, we didn't talk about this, but that's a voltage standing wave ratio, which is the match of the antenna to the cable, which should be close to 1, which is reasonably good. Has a weight and the wind load and all this stuff. It gives a polarization. Remember, we talked about the polarization. It has a vertical polarization, so the lines, the E field that comes out here is vertically polarized. Down here we see the radiation pattern, vertical and horizontal. I could also call this here elevation, and this one I can call azimuth. It would be the same as calling it vertical and horizontal. Good. Now, you can design antennas such that they radiate more or less, not perfectly, as I said, but more or less the same amount of power in all directions. And then this is known as an omnidirectional antenna or a low gain antenna. Why is it called a low gain antenna? Well, when an antenna radiates in all directions the same, it doesn't have a preferable direction. And since the power doesn't come from nothing, it has to distribute the power over the whole area. That means not much power goes in one direction. It has a low gain. Alternatively, you can design antennas that have spot beams or high gain antennas. They bundle the power in one direction, and they have very high gain in one direction, but on the downside they have very low gain in other directions. They are known as high gain antennas. Depending on your application, you use omnidirectional antennas or high gain antennas. I can show you here. So this would be a typical omnidirectional antenna, and that would be a high gain antenna. And you see the high gain antenna radiates more in this direction. So here at this area, you receive much more power than you receive for the omnidirectional antenna. However, you have the drawback that you do not receive anything in this area here from the high directional antenna, whereas this you can have reception everywhere around. And that means when you want to broadcast a signal, FM broadcast, use a omnidirectional antenna because you want to have everybody to be able to listen to you. Or when you have to, when you need a point-to-point connection, I want to have a connection between Hamburg and Bremen, then I use a high gain antenna because you're not interested in people in Delmenhorst listening to your signal. High gain antennas need big areas. That's a rule of thumb, and we are not going into the detailed theory of antennas, but and later on we have an equation that explains that. When you have a high gain antenna, you have to build a big antenna. The bigger the antenna, the more gain you get. That's a typical example here of a high gain antenna. I think it's the one in Usingen in Bavaria. This is a satellite ground station. And with this satellite ground station, you have an antenna that has, I don't know, something like 20 meters diameter or so. And this antenna bundles all its power in basically one direction. So when you want to communicate with a satellite or even with a space probe in a big distance, then you should use these kind of antennas because they give you a high gain. High gain, as we see later, gives you a bigger signal in reception and in transmit. Disadvantage here, you only receive one single satellite. You cannot see anything else. Whereas a typical low gain antenna is small. This is here an antenna on a cell phone. And this is my last picture I could find for a cell phone that has an external antenna. Nowadays the antennas are built in. And typical for low gain antenna, as I said, they are small. And those antennas radiate in all directions the same way. For a cell phone you need that because it should not depend on your direction of view or how you hold your cell phone. You always want to receive and transmit the same amount of power in all directions. When your base station is here, you want to transmit in this direction, but when your base station is down here, you want to transmit in this direction. It should be independent of the way you're holding your phone. On spacecrafts, you always have high gain and low gain antennas. Let's see if we can, I'm not sure, maybe there is a high gain antenna here. And, oops, sorry. Oh. let's draw it with white here. Let's see if this works. So you have a, now the white doesn't work for the marker. Yeah, we have a high gain antenna here. So maybe switch back to my, so we have a high gain antenna here. And this high gain antenna is for communicating with the ground station. And since you have high gain, you get a good link. In addition, you have here and here low gain antennas. Those low gain antennas are also required, and they have one simple reason. When the satellite for some reason rotates in the wrong direction, and this high gain antenna looks into deep space and not down to the ground, there's no way you can contact your satellite over the high gain antenna because it looks in the wrong direction. However, using a telemetry signal, you have to give the command to the satellite to say, hey, let's turn around again, but you cannot give the command if you do not have a connection. And that's where these low gain antennas come into play. They receive a signal from every direction, and they are usually used for the telemetry, tracking and control, the TTC signal. And since TTC signals have low data rates, they just have commands like please turn around by 90 degrees. They do not need high gain because they only require a low amount of power to operate. So that's why actually every satellite has a low gain antenna for the telemetry link, because this one is independent from the orientation of the satellite. In our lab at the university, we have a room which is anechoic and also it's shielded among other radiations. And in this room, we can rotate our antennas and we can measure the pattern of the antennas. This is a pattern actually measured of a real antenna in that room. And you see clearly how the antenna works. It has a main direction of radiation here. Maybe let's do blue or something like this here. It's the main direction of radiation here in this direction, where it radiates a lot. And then it has some other directions. For example, here this direction. In this direction, it doesn't radiate anything because it's a so-called zero. And then at other directions, you see, interestingly, for this, for example, in this direction, 315 degrees. That's my azimuth pattern. No? You see that you radiate minus 35 dB compared to the minus 22 dB here. Still a reasonable amount of power you radiate from this so-called side lobes here. That's very typical for antennas. That happens that from the field theory that you have a number of so-called side lobes here where it radiates even though you don't want it, but that's a fact of life you cannot avoid. When you unroll this polar plot, you actually can also see the same diagram in a Cartesian plot, and it looks like this. Some people give this Cartesian plots, some others give the polar plot. The polar plot is more intuitive. In order to define the width of your so-called main lobe, here, this one is the main lobe, this green here. In order to define the width of that main lobe, there's a rule. So how wide is my main lobe? It's difficult because it slightly degrades over distance. And people came up with a rule, and it's a very simple rule. They measure the maximum, let's go here in red. They measure the maximum radiation and then go left and right until you are 3 dB down. In these two directions, there are 3 dB less radiation than in the main direction. So between here and here, I have 3 dB. And then you can define two angles, one here and one here, where you are 3 dB down. And this angle, it's called the 3 dB beam width angle. I have another slide in a second coming up. You also have an elevation angle. That's my elevation pattern. It looks quite different, but still you have these typical side lobes and main lobes. The side lobes are almost the same size as the main lobes. They come down to 3 dB. That's why you have 2 more markers. And you see here that this is my maximum. And here we are 3 dB down. Here we are 3 dB down. And that means my opening angle, 3 dB in this direction, is considerably larger. No? But still we have an angle. So it goes from -11 to +22 degrees. So here's a slide again explaining the definition of the beam width. The beam width is defined as angular beam width between the points where the directivity reaches half its maximum. Now, here's my maximum power. Here it's half. Here it's half. In dB, half is 3 dB. That's why it's called 3 dB point. And then you define these angles and you get your so-called 3 dB beam width. When you the 3 dB beam width, is related to the maximum gain. The narrower your main lobe is, so the smaller the 3 dB beam width, the bigger your G max is, because you concentrate the power more and more in one direction. And a guy named Krauss, he is a famous antenna engineer, developed a formula which roughly gives the relation between my gain or directivity, which is used in the same manner in this slide, which defines the ratio between my gain or directivity and my beam width in elevation and my beam width in azimuth direction. Remember, we have to define 2 beam width. When I go back here to my measurement, no? In azimuth, I have this beam width. In elevation, I have this beam width. And then these 2 beam width I can put in my formula. And when I use degrees, as I used in my measurement slide, I have to use, I have to convert 4 pi rad into degrees, and this becomes 41,000. So when you plug that in, you can actually get the gain of the antenna by measuring the beam width. Approximately. That doesn't work for low gain antennas, it only works for high gain antennas. So for example, for my Hertzian dipole, which is a low gain antenna, it doesn't work. Here the example, let's go back. We have, let's see, I use maybe purple. Minus 5.7 degree to 5.7 degree is my theta beam width. Minus, so the beam width is 11.4 degrees in azimuth direction. In the other direction, it's minus 11.5 to plus 22.9. So it's 22.9 minus plus 11.25. So my beam width is 34.4 degrees in elevation direction. Plugging in these values in my formula down here, I get 104.55. Converting this to dBi, I get 20 dBi antenna gain. That's how I can quickly approximate my antenna gain from one measurement. There are other methods to measure the gain. The actual gain, I think it's 18 dBi. So it's close, but it's not exact. Okay. Last quantity I define here today is the so-called EIRP. The EIRP is the effective isotropic radiated power. This number is a fictitious number. You cannot actually measure it exactly, or you cannot measure it directly. You only can do it indirectly, and it defines a fictional power that operates the antenna. And the idea is the following, and I hope I get the explanation here. When I have one gain antenna here, which is a very big antenna, let's make the line smaller. When I have one antenna that radiates mostly in one direction, then, and that's something I forgot to mention on my slides, my received power flux density S is the amount of power flux generated by an isotropic antenna, 4 pi over r square. Here's my P transmit somewhere, no? I stuff my P transmit into my antenna, it's radiated, and up here when I look through a little window I see a power flux density of, well, isotropic, it would be PT over 4 pi r square. Since this antenna has gain, and my gain defines the factor it transmits more in this direction, then my actually power flux density becomes G times my PT over 4 pi r square. Very important formula. Let's mark that. So. Now let's compare it to an isotropic antenna. Oops, let's make it in black. Well, when I have an isotropic antenna, let's draw it like a ball here, and I feed in some power, then this antenna radiates the same in all directions. So that means here I receive another power, and this power I receive here is S. Oops, let's go back to black. This is S is equal to P of the isotropic antenna divided by 4 pi r square. So here I measure this P of the isotropic antenna powered over 4 pi r square. Makes sense. Now, when I compare these two received power flux densities, I can make it such that those two are the same by increasing this iso power here. Is this, well, when I use the same power, obviously you get the same, you get less S here than you get up here. When you increase this iso power down here, at some point you receive the same power flux density in both cases. And that means for anybody standing here or here, when you receive the same power flux density, you cannot distinguish, is this power generated by an isotropic antenna with a certain amount of power, P iso, or is it generated by an antenna with high gain and a much less input power. So, since you cannot distinguish, for the receiver it doesn't matter if you have case 1 or case 2. Only important is that, well, so when in order to receive the same power, you see from my equations, P iso must be the same as G times PT. So when I have a power which is the same as G times PT, in both cases I receive the same amount of power. And for my receiver it doesn't matter if the transmitter transmit with a high gain antenna and a small power or with a low gain antenna with a high power. Only important is the product between G and PT, because then you know everything you need to know. And that's why this P iso is called the P iso is known as, and I take this out now. The P iso is called the EIRP. The equivalent isotropic radiated power. And this is identical to this, so that's why we can actually make this an important formula. EIRP is a power measured in watts, which describes the required power to power up an isotropic antenna to give you exactly the power flux density you have in the real case. And the real case is the gain times the PT. If you don't get it exactly now, it's not so important, but you have to remember that formula here, which is important. The equivalent radiated power is my gain times my transmit power. And when I design a receiver, I want to know that value. I do not need to know the gain and the transmit power. It doesn't matter to me. I only need the power. I need the product here. This product here I need. And that's why you can also write this formula here in a different manner. Black. So S is equals to EIRP divided by 4 pi r square. So when I build a receiver, I want that formula, and for that I need my EIRP. Good. Okay, we learned a lot this time. So, and here I just put it on one slide. EIP is not a real existing power, but a value for calculations, and the EIP is related to the real fed power of the antenna by that value here. I use Gmax here because usually you orient your antenna for the maximum gain, and that's why without accuracy you can say EIRP is Gmax times P transmit, or PS in German. So I would call it PT. So, where PT is the transmit power. Small example. Again, now we have a mobile phone base station, and this base station has an antenna with 17 dBi gain, similar to the one we have seen, and a transmit with 10 watts of power. Well, since 17 dBi is, since 17 dBi is the same, maybe we have to make another lecture on dBs. 17 dBi, how much is this in absolute value? Well, 17 dBi is 20 dB minus 3 dB. And now when you remember from bachelor, you can convert this and then multiply in the absolute domain. 20 is factor 100. 3 is factor 2, but it's minus, so it's 1/2, so we get factor 50. So 17 dBi is nothing else but factor 50 in absolute values. That means when I have 10 watts here, that gives me 500 watts. And since I use the exact value, it's 501 watts absolute power as EIRP. Maybe I draw that again down here. So EIRP is equal to P transmit times gain. P transmit is 10 watts times gain was 50. That gives me 500 watts. And as I said, for the mechanical people, we haven't talked about dBs. Maybe I should put another lecture in dBs in for the next week. And when you can do it in the dB domain by saying EIRP in dB watts is P transmit in dB watts plus gain in dBi. As I said, we haven't really talked about that. That's why I don't have the answer here. So maybe we do it next week. How this is done. So important this is part here. No? So 500 watt means, important is the result here, 500 watt means, 500 watt means, here. Oops, 500 watt means that when you are, let's maybe take this out here. As I said, we haven't done that yet, so we do it next time. Means, let's draw a little figure again. Here's my base station tower. And here's a guy with a cell phone, and he receives a signal. And the power flux density he receives is S times, it's equal to EIRP divided by 4 pi r square. Now this is distance r here. No? So for the guy who received this, it appears that this antenna here radiates with 500 watts in all directions, even though in reality it transmits only with 10 watts and a gain of 17 dBi in this direction. For the receiver, it doesn't make a difference. That's why the EIRP value is so important for us. Okay. As I mentioned before, you also have to look at something like side lobes. When we have an antenna that has a typical radiation pattern like this, then you can find this here being the main lobe, and then you also have here a side lobe, and the side lobe should be considerably smaller than the main lobe. Otherwise, you run into problems when you want to look at one satellite only. I always make the same mistake here. That first I do this and then I do this. So, when I want to receive a satellite in this direction here, and there's another satellite here which I don't want to receive, then my side lobe is a problem, because here I receive a signal from my satellite, and there's another satellite, and this is also received from the side lobe. But since my side lobe is 40 dB less than my main lobe, the signal is 40 dB smaller, which is factor 10,000. So a side lobe attenuation of 40 dB is good. You don't want a side lobe that it's close to the main lobe, because then you receive from directions you don't want to receive, and that may cause problems. Okay, so that's it about the general aspects of antennas. And next is talking about receiving antennas, which are in general the same as general antennas, but there are some specialties to it, and that's what I'm going to split into a different session. That means that's it for now, and I hope you could enjoy the lecture, go back and forth to look at things again, and also look at the problems. And next week we also, in our live session, we're going to do some problems about that. Okay, thanks for listening.